From now on, we are going to explain how the multiple threads can share a single CPU. The important responsibility of operating system is to provide an illusion that there are multiple CPUs and individual processes can have its own CPU. There are a single CPU here, and then assume that there are multiple threads running each own application. This is web server, and this is MP3 player, and this is word process. Then all these processes shares a single CPU so that each of these processes can be executed in parallel. User has an illusion that each of these processes are executing its own CPU. In providing such a capability, the important part is performance and control. The meaning of performance is that how can we implement virtualization without adding excessive overhead to the system. In this example, we have to switch the CPU over multiple different processes. From here, at time t1, it executes web. And then later, and sometime later, at time t2, it executes MP3. And at time t3, it executes word process. So in the timeline, from t1 and t2 and t3, then from t1 to t2, web is executed. And from t2 to t3, MP3 player is executed. Starting from t3, word process is executed. Problem here is that from at t2 and at t1 and even in t3, we have to switch an execution from execution of web to MP3 player and from MP3 player to the word process. How we can switch the execution of a process from one to another is an important concern, and it has to be implemented in a very efficient manner. That's what we call performance. The second issue is control. There are three processes here. Here we have chosen web as a first process to execute, and MP3 as a second process to execute, and then word process, third process to execute. However, there are three factorial ways of executing these processes. So what is the best way to select the next process to run? In here, we first choose 1, 2, and 3. This was the order of execution in our environment. What about 2, 3, and 1? What kind of strategy the operating system should choose to execute a set of process execution? That is a very important aspect of CPU scheduling. Very primitive way of running a process is called direct execution. Direct execution. There are two important terminologies here. When we run a process, we just create, it's very similar to fork and exec. It creates an entry for process list. And then it creates a memory for a program to run. And then it loads a program from the disk to memory. Then it sets up a stack with the parameter it wants to execute. And then it prepares a register and it calls main. So this one is very similar to goto instruction. After the user program finishes execution, then it returns or calls exits. Then operating system is responsible for freeing the memory of the process it just allocated. And then it removes the process structure from the process list. Operating system is running, and then it decides to run a process. Then it just prepares the memory address space and initializes the registers, and then transfers the control to the application program. And then application program runs, and when it exits, it goes back, and operating system continues to execute. So this part is what we call user program execution. User program execution. There is not much things happen between executing an operating system here and then executing a user program at this point. It just transfers the control to the user program. User program have the same privilege as an operating system in this execution protocol. So it can access any of the disk space. it can access any of the address space. So operating system is just a library. Here, you have to pay attention to the fact that user program has the same privilege level as the operating system does have. Operating system is a powerful software. It can access any part of memory address space, and it can do anything with the hardware. There are two issues we need to take into account in direct execution. First one is that user can make a mistake. User can do the wrong thing. Consider this piece of code. It defines a pointer, allocates 0 to the pointer value, and then it tries to save 1 to the whatever address the pointer is points to.
Basically, this program saves a value 1 to the address 0.
In virtual address space, a certain section of process address space is reserved only for the special usage. Only the operating system is allowed to access those address region. If operating system transfers all its privilege to the user process, then user process can do anything it wants to do. And in this program, the user program is allowed to write the special value here to whatever address pointed by the pointer, which is 0. So if a single process overwrite the value to this region, then that can affect entire operating system's behavior and may lead to crash of the system.
Second thing is how to regain control of the CPU from the user process.
If the operating system directly transfers control to the user program, then operating system has to wait until the user program finishes and transfers the control back to the operating system. There is no way for the operating system to stop the user program and to control the CPU back. So consider following code. What if the user program assigns I to -1 and the user program executes a while loop that continuously works while I equals less than 0? Then there is no way for the user program to get out of this infinite loop, and operating system will be waiting forever for the user to finish its execution. This user program monopolizes CPU, and basically the system stops working. In this section is that there are two issues. The first one, we have to have a mechanism to protect a system. And second one, control the execution. The first one is about controlling the memory access. And then second one is to control the execution. So in these two topics, issue 1, we'll deal with the mechanism to control the access of a process over memory address space. The second issue, we're going to control the mechanism to control the process execution along the time axis. So this is the issue of space versus time. The approach to control the access to this address space is limit the operation. A process wants to execute some privileged operation, such as accessing the disk, or it wants to get more CPU cycles, or it wants to get allocated more amount of stack space or heap space. Because disk and memory, those are shared by all the processes in the system. We have to be very careful to enable the process to get an access to this resource allocation. A process wants to create a file, or a process wants to expand its stack or heap space. But those resources, disk I/O, disks, and memory are shared among all the processes, and we have to be very careful in allocating these hardware resources to processes, because we cannot simply grant all the requests from the user process, because then it will affect the execution of the rest of the processes. What if a process wishes to perform some kind of restricted operation, such as issuing an I/O request to the disk, or gaining access to the CPU or memory? There are two approaches. First, grant everything. The second one is operating system takes full control of the hardware resource and ask the user to make a request to the operating system. And once the operating system gets a request, operating system makes a careful decision on every aspect of the request the user process has made, and then it decides whether to grant an access or not. That is what we call system call. In that kind of operating system, the operating system defines two modes. First one is user mode. The second one is kernel mode. If the process runs in the low privilege level mode, which normally is called user mode, then it can access only the specific memory address space. In kernel mode, operating system allows the user process to do anything it wants to do. The operating system can switch the process from one mode to another based upon the request. There is an important concept of system call. This is one of the most important inventions in operating systems history. Kernel expose some key operations to the user program, such as reading a disk or creating a file at the disk, or creating a process, and allocating more memory, such as SBRK system cores. User has to ask the operating system to perform these operations on behalf of the user process. It's something like you go to a bank and there is a safe. Let's say this is safe, and user asks for $100, and then you ask the teller to withdraw $100 from your bank account, and then the teller goes to the safe, and then it gets $100, and then it hands over the $100 he just removed from the safe to you. None of the bank directly allows you to go to the safe and get the $100, even though you have $100 in your account. So no bank allows that. So this is the operating system service you ask. So when you need to access the delicate resources, you have to ask the operating system